Project proposals are going to be due today. There's no extension for that. So please submit your projects. I think there were a few questions about, can it be like a page and a half? Sure. Just don't make it like a 10-page project submission, right? If you need to go over one page a little to finish your thoughts, you're more than welcome to do that, okay? Maybe a page and a half, but just don't go over because it's just going to be a lot of work for TAs to go through your project proposals. Let's see, what else? The last assignment is going to be handed out, I think, next week. We're still targeting Monday. Maybe we'll release it on Wednesday. I don't know, depending on when it's going to be ready. But let's aim for next Monday. The last assignment is going to be out. Your mid-semester grades. I guess you will see your mid-semester grades, and the mid-semester grades are going to be primarily based on your first homework and your midterm. So don't. It's like it's a little bit more on the lower bound, because your midterm is probably the toughest part, because most people do well on the assignments. So take it with a grain of salt, right? Don't, like, if you see a grade that's below what your expectations are, is because of your midterm. Don't feel too bad. Typically the grades will go up because we haven't taken into account your second and third assignment and your projects. Okay. Also, I believe that sometimes by Thursday or so, you will see your midterm grades. And what I'm going to do next Wednesday is we're going to go through the midterm, and I'm going to show you some of the common mistakes that people have made. Okay? So I'll show you the solutions, but I'm also going to show you some of the mistakes so that you guys wouldn't bother TAs too much with regrading. So I'm going to show you, what are the common mistakes people were making and where the marks were taken off. Okay? For the midterm, based on distribution of the grades, a number of people did really well. I think there are like a certain fraction, pretty large fraction of people that basically aced the midterm, and there's a fraction of people who kind of failed. So, so you kind of like will see overall distribution of the midterm grades. What else? Let's see. Projects, you should be thinking about your projects. Hopefully in your project proposal, you already have something that you are thinking about working towards. You have now, based on your project proposals, we'll give you some feedback. You're basically going to have a month and a half to finish your project, which is not a lot of time. So you should really start thinking about, if you haven't done that yet, because I know a lot of students are asking, so what should my project be? And the project proposals are due today. So generally, try not to be in that situation, because if you start working on your project a week before it's due, and it's going to be due in early December, right? I think December, when did we say? December 4th, December 6th, or something like that. But don't, start working on your projects today. At least the key components in your projects, you should really think about the problem that you're trying to solve. But more importantly, the data sets that you're going to be using, because you can think about a terrific problem, but if you don't have data, then you can't really do the project, right? So there are usually students who really think big and think, we're going to solve this big problem, but if there's no data, there's not much you can do. So think about the data, think about the problem, think about what software you're going to be using. If you have access to GPUs, you're more than welcome to use GPUs. But if you don't try to do something ambitious. I'm going to be training this gigantic speech recognition model on 10 years of data, and then do you have access to compute? No, it's my laptop. Then you can't really do that. So try to think about a self-contained projects. The projects can be ambitious. But at the same time, if you don't have compute resources, you're more than welcome to use a subset of the data, right? Is there anything else? So from now on, your second assignment is due. You only have the third assignment and projects, and we only have a month and a half left. So start thinking about your project, because it's going to be a major part of your grade. Okay? Any questions? And also feel free to talk about your projects to the TAs, because TAs have office hours. I think we have like 4 office hours a week. So talk to the TAs. These are PhD students. They worked in this area. Also, I have office hours on Mondays from 11 to 12. You're more than welcome to come and talk to me about your projects. Okay, so today what I'd like to do is for the next couple of lectures, we're going to go and look at sequence-to-sequence models. These are kind of inspired based on language modeling that we've seen in the last class, but we're going to dive deeper into those models. And if you're interested in kind of this kind of material, the slides that I'm using, a lot of the slides that I'm going to be using are based on sequence-to-sequence ICML tutorial this year. There is a site that you can visit. It was done by Oriel and Navdeep, and they graciously agreed to share the slides because they put a lot of work into preparing that material. These models are quite recent, maybe just 2 to 3 years old. But I felt that for us, it's going to be important to look through these slides. And also your homework, your third homework, you will be building a language model. So you will kind of get familiarized a little bit with these kinds of models. Okay, so there is a website. You're more than welcome to look at the website. And it's an excellent, excellent tutorial. I think it's like 3 or 4 hour tutorial. Okay, so sequences. We'll look at the sequences, word, letters, we'll look at the speech, we'll look at the images or videos, right? These could be thought of sequences, programs, and also sequential decision-making, reinforcement learning. In fact, I think next semester I'm going to be teaching in a reinforcement learning class, which is going to be diving deeper into the sequential decision-making and deep learning. Here's an interesting quote from Geoff Hinton, which is, again, was in this tutorial, so I thought I'd put it here as well. And reads as follows: 50 years ago, the fathers of artificial intelligence convinced everybody that logic was the key to intelligence. Somehow we had to get computers to do logical reasoning. The alternative approach, which they thought was crazy, was to forget logic and try to understand how networks of brain cells learn things. Curiously, 2 people who rejected the logic-based approach to AI were Turing and von Neumann. If either of them had lived, I think things would have turned out differently. Now neural networks are everywhere, and the crazy approach is winning, right? So it's just an interesting quote from Geoff Hinton. Something to think about. But if we look at the classical model for sequence prediction, so sequence predictions was always handled as a structured prediction tasks, right? For example, we would look at on some conditional independence assumptions. There's been a bunch of very successful approaches like Dagger were based on supervisory signal and auxiliary information. So for example, this is a figure from, I guess, was done at Microsoft, where you have some observed, you pass it through the deep neural net, and then you have these sequences. And the best way people would do it is they would use HMMs, right? So this is typically a very classical model for modeling sequential data. You put it through HMM. People were also looking at Markov random fields and conditional random fields and structured prediction. That's kind of, and it's today, it's a big sort of big area of research. But the 2 key ingredients for modeling sequences over the last few years that's popped up is this notion of embeddings, neural embeddings, right? So you take your word vectors, so you take your sequential or parts of speech or parts of phrases, and you embed them into some continuous representation, right? Precisely what we talked about in the last class, taking words and getting the continuous representation of those words. And combining these ideas with recurrent language models. So these are, you can think of them as recurrent neural networks, where you have some hidden states like the cat sat on the mat, right? And given a sequence, you're predicting cat. And then again, given cat, you're predicting set. And then given set, you're predicting on, right? So these are recurrent neural networks that basically read a sequence and also make predictions. So these are the 2 key ideas that we will see. Now let's remind ourselves on the language models, right? Something that we've covered in the last class. The language models is really the idea of modeling these conditional probabilities, right? And I believe in your last homework, you will actually build one of these models. You will train it, and you will learn word embeddings as well. So you'll get a little bit of experience into these models. So here, given some context, you're trying to predict the target, right? So for example, given the context of the cat set on then you're predicting Matt, right? And this is what you're seeing here as a conditional probability. Conditional probability of WT, which is Matt, conditioned on the context, right? And then you can say, well, now these are the probabilities that you're trying to estimate. The cat set on the rod, the cat set on the hat, and so you can see these are probabilities that I assigned. The cat set on the dog, 0.01. There's some probability that might happen, but the cat set on the set or the cat set on the robot, well, maybe on the robot there's some non-zero probability, and so forth, right? Or the cat set on the, right? That's typically grammatically not correct, and you don't observe this, and hopefully your model will assign an almost zero probability to this. If we look at the traditional n-gram models, what is n-gram models are doing? These have been very popular, and even they're popular today because these are very, if you have enough data, there's very powerful models. The idea is to construct a matrix, and you're just basically counting how many times word and the context appears versus how many times just the context appears. So for example, the cat sat on the mat, the cat drinks milk, the dog chases the cat, paws on the cat, and so forth, right? So bigrams and trigrams been quite popular. The problem is that you can't really build a 5-gram or 10-gram model, right? Because the probabilities, you can't really estimate probabilities correctly given the larger context. And there's a lot of smoothing operations that people have come up with, and systems like, for example, Google, they're using 5 grams or 6 grams because they have so much data. And if you've seen, some of that data, then it's easy to estimate the probabilities, right? So it's almost like nearest neighbors. The more data you have, the better your nearest neighbor is going to be working, right? So here's, what we're trying to do is we're trying to here actually do the approximation. We can say, well, the joint distribution of all the words is approximately equals to bunch of conditionals, right? But the conditionals only depend on the context of size n. Whereas if you wanted this approximation to be equality, you would actually have to condition on the entire context, right? So if I wanted, this is just by the chain rule of the probability. If I look at the joint, notice that I can model the conditional on the past history, the entire past history. Whereas what you're trying to do is here, you're just approximating it by conditioning on some context. And context is typically of size 5 or 3 or 4, whatever that parameter is. Right? So here you're just estimating these probabilities. And obviously one thing you can do is you can generate from this model, right? You can sample from P of W1, which is a distribution over your vocabulary. For example, it could be uniform, or if you fit it to the data, some words tend to appear more often at the start of the sentence. You sample from that. So for example, you sample the, then you sample the next word, which could be cat, you sample the next word, and so forth, right? So you can, these models are generative, right? You can actually generate a whole sentence. Now, one of the key insights over the last decade people thought about is this idea of vectorizing the context, right? So the idea is to vectorize the context, so you can see that here, when I look at this conditional probability will depend on some function f that takes the overall context into account. And this is where recurrent neural networks or neural language models are coming in, right? Because what you have is you're representing let's say you have some vocabulary, you're representing it in some 10-dimensional, 100-dimensional in this case, feature space, which is your Z representation, and then you can incorporate all this context into account and try to predict the distribution over the next word. So the idea here is as follows. Let's say I have I have some representation here, which is given by, I guess, given by u here. And then I also have some z at t minus 1, right? So this is some previous hidden state. Think of it as a hidden state of a recurrent network. Now I say cat, right? Again, I look at my hidden state, but I also look at my zt minus 1. And then I look at zt, I think it should be zt and so forth. So I'm always looking at the previous context, oops, right? In order to produce the distribution of the next word. So again, the idea here is that, you know, you're always keeping overall context and vectorizing it. We'll make it more precise when we go through the definition of what these probabilities are. But remember from our last class, right? From our last class, we were constructing a neural language model. This is essentially a neural language model as well, right? Now, depending on how you link these things together, it could be a recurrent neural network, it could be linear, it could be nonlinear and such. There's a lot of different variations of this model. Here, the idea is that you add the previous context, you add this new word, you add them up, you pass it through this some nonlinearity, it gives you the hidden state. And given the hidden state, you pass it through the softmax to compute the distribution of the next word. And that's exactly the neural language model that we've discussed in our last class, if you go back to the definition. So, what is it that we're optimizing? We're really optimizing the joint distribution of all the words in our sequence, right? So I give you a sentence, or a paragraph, or a document, and what I'm really trying to do is I'm really trying to maximize the joint probability of all of these words appearing together, right? I can break it down into conditionals, and then we're making approximations by conditionals only depending on specific context, maybe context of 5 or 6 words, right? And W here is sample from the data distribution. So these are your sentences that you observe, or sequences that you observe. Any questions? So for the language model, we are always optimizing the joint probability distribution of all the words that we see in a sequence, right? And one thing to notice is that this joint distribution, it's not, you know, if we were working in IID assumption, words are independent of each other. We can just say it's the product of individual words. Take the log, and it's the sum of individual words, which is what's typically happening when we work with, you know, classifying images, for example. Here, the next word depends on the previous word, so it's really the sequential modeling. Now, recurrent neural language models. So, if you think about recurrent neural networks, right, what is a recurrent neural network? I believe we've covered it a little bit in our last class, but it really is, you have some hidden state, H0. You have some observation, like the. You know, let's say I give you a sentence, the cat sat on the mat, right? I see the first observation there. I combine the observation and the hidden state, add them together, pass them through nonlinearity, and then I'm trying to predict cat, right? So the output of the neural language model is the prediction, which is again just a softmax. But here I'm trying to predict cat, right? And then at the next time step, I see cat. And again, I'm combining the hidden representation coming from the previous state with the cat. I combine them, and I'm trying to predict set. Again, given set, and so forth. So what you see at the bottom is my observation. What you see at the top are my predictions, right? So in many language models, you're trying to predict the next word. For example, if I say you, the cat, your next prediction is going to be set, right? Think of it as time 0, or time 1, time 2, time 3. So that's exactly what, you know, is happening, right? Everybody sees that? Fairly simple, fairly straightforward. But now, when you're training these models, you basically have to backpropagate gradients, and this is the backward pass. You have to backpropagate gradients through the entire model, right? So you have hidden to hidden connections, you have visible to hidden connections, and you have hidden to output connections, right? And if you look at any particular slice, the cat is the input. What you're trying to predict is set. If you look at this slice, then the cat set on, and you're trying to predict the, right, and so forth. So in this case, you're basically going to be combining gradients from every single prediction and backpropagating it through the entire model, right? Does that make sense? Okay, one more thing that I want to point out here is that when you're making predictions, right, what you do is you say, well, first of all, given the word the, sample the next word. And you can sample cat, or you can sample dog, or you can sample the, any other word. Given what you sampled, you condition, let's say you sample cat, you condition the cat, and then again, you make a prediction. You sample what's your next best prediction, right, and so forth. So that's how you would generate a sentence, or you would generate a sequence of sentences from this model. There's a lot of papers on sequence modeling. As you can see, there's a whole bunch of different papers. I think that back in 2013, 2014, there were a few papers on trying to use recurrent networks for language models. If you're interested in looking at some of those papers. Now, what's the key behind sequence-to-sequence models? The idea is that now, instead of having a single sequence, maybe just a language model that you're trying to model, you actually have an input sequence and you have a target sequence. Okay? So think of, for example, machine translation system. The input sequence could be French, the output sequence could be English, right? Or think about speech transcription, which is I say something to the device. So the input sequence is going to be just a bunch of speech signal, and the output would be a sentence, what I just said. So you're transcribing from speech to language, right? Or you could be, there's a whole, the whole family of different models you can imagine going from sequence to sequence, and we'll see some, a number of examples. Now, one of the things, when we think about decoding in these models, right? So for example, given some a sequence, I'm trying to predict the next sequence. And let's say I'm trying to get the best possible output sequence. One thing you can do is you can sample, as I mentioned. Given some context, you sample the next word, right? Or given some context, like if I give you a French sentence, I can sample the English sentence, because I have a bunch of softmaxes. But what people found out is that what you'd like to do is you'd like to actually find the best sequence given the input sequence, right? And this is something that's known as a beam search, which is you have multiple partial hypotheses and you try to pick the best one, right? How many of you have heard about beam search? A few. Okay. So the idea is the following. Let's say, I pick my first word, which could be I or my. Okay? So these are the most probable words that your sentence starts with. Let's say, according to some empirical distribution, these are most probable candidate words. Then you can expand and sort. So you can say, what's the next word? Well, if you have two of these hypotheses, for each one, I can look at the next prediction, the next softmax, and pick the best, maybe the best three choices, right? For each one, for each of the hypotheses. So I can say, I decided, I thought, I tried, or my decision, my thinking, my direction, right? So now you have 6 candidates. You can compute the probabilities for each of those 6 candidates because you have softmax probabilities, right? So you compute them, you can re-rank, and you prune, and you only maintain the top 2. So these are the most probable ones. I decided, or my thought, and so forth, right? So whenever you do translation or whatever you do language modeling, like given, for example, I've shown you some examples, I'll show you some examples of caption generation. Given an image as an input, you're trying to generate the sequence. Well, you can sample from the model, or you can try to find the best possible sentence, right? And the best possible sentence is done via the beam search. It doesn't guarantee that that's the best one. It's still a greedy heuristic. But nonetheless, it typically produces way better results. Code, if you're interested in looking at some sequence-to-sequence models, there is a code. I think it's in TensorFlow. You're more than welcome to look at the code. This is the link to the code. There are explanations of how you can build sequence-to-sequence models and so forth. There is a code in TensorFlow. There's also code in PyTorch, so depending on which package you want to use. Most people don't really use some of those packages because computing the gradients and backpropagating them efficiently through these recurrent neural networks is a little bit hard. Mathematically, there is nothing particularly difficult because it's just, you can think of recurrent neural network as just a deep neural network with tight weights. But these packages do allow you to have a very efficient implementation of backpropagation. Now, let's just remind ourselves, right, what we're actually doing. And we're going to talk a little bit about this. So your model runs, your loss goes down, whatever you're optimizing. And then, let's say you overfit. Well, if you overfit, you try to, regularize, you try to find best architectures, you try to find the best hyperparameters. And then, you regularize, you overfit, and try to regularize more, and so forth, right? So there is and what we will see through some of today's and I guess next class, in our next class, is that we'll see a lot of people are trying to figure out what are the best architectures to use, right? So some tricks. And later on, we'll see how do we do optimization. But just some tricks to think to yourself. What about long sequences? Say I have a very long sentence, right? And what we've seen so far is I have this long sentence, you compress it down to some hidden state, and given this hidden state, you try to predict, a sentence in French. But if it's a long sentence, very hard for these models to, have enough memory to figure out, how to compress this entire sentence. So if you have longer sentences, then we're going to talk about attention mechanisms that allow you to adaptively change or to adaptively figure out which part of the input sequence you should be looking at to make a prediction. So attention-based models have come up in the last few years, and as some people joke, it's all about attention now. What's the best attention mechanisms? And they do give state-of-the-art results on machine translation and neural machine translation and speech recognition. Or you can also think about bigger state. Some people have said, well, if we actually have larger hidden states, maybe if it's longer sequences, we can still preserve the information. If you can't overfit, remember when we looked at deep neural nets, if you can't overfit, you might want to think about bigger hidden state. So if you're not overfitting without any regularization, your model is still weak, right? For whatever size data you have. You should think about building bigger models. And people have looked at deep recurrent neural networks, these called deep LSTM models. We have multiple layers. People thought about having skip connections and all kinds of crazy architectures that people are coming up with. If you're overfitting, obviously dropout is a good strategy. Ensembles and is it standard things, more like engineering things to do. Tuning, I guess it's keep calm and decrease your learning rate. That's more of a initialization of parameters is critical. So in sequence-to-sequence models, typically people use uniform from minus 0.05 to 0.05, right? Much like, as a joke of what your learning rate should be, your learning rate should be 0.01 or 0.001, right? So the other thing that we didn't talk much about, but this notion of clipping the gradients. Right, so this is more for optimization, which is if the magnitude of your gradient, the norm of your gradient becomes large, then you just do scaling. And that's a hyperparameter that you have to choose. If your gradient becomes larger than 5, sometimes people choose it to be 2 or 3, then you're basically clipping the gradients, right? You're basically saying that they cannot be very high. In practice, just from engineering standpoint, it helps a lot doing gradient clipping. Okay? Okay, let's look at some applications. Some Some application of these models. Machine translation is one very big big area. So here's an example of sequence-to-sequence models where you basically have a input sentences in English, output sentences in French. You're just training this model, right? So again, remember, how do we train it? We read the whole sequence using recurrent nets. We have the hidden state, and then from this hidden state, we try to predict the French sentence, right? Very simple. And you've looked at the ensembles, single forward ensembles, and so forth. But what's interestingly, your model was able to find these interesting regularities. So for example, if you look at the embedding of the word, of the sentence, Mary admires John, and you do, in this case, I think it was t-SNE projection, so your projection of this high-dimensional vector, which I think was 5,000 to two-dimensional space, what you find is you find things like Mary admires John, Mary is in love with John, or Mary respects John, right? You have these sentences on this side. But interestingly, John admires Mary, and John is in love with Mary. They're mapped to somewhere else in this space. So the model is figuring out that John admires Mary and Mary admires John are two very different sentences. So that was a little bit surprising, right? Because if you use like bag of words or something simple as such, right, there is no way to distinguish these two sentences. It also sort of figures out that admires and in love and respects are kind of, a little bit distant from each other. It also finds it's just based on translation, right? You're translating from English to French. Or for example, I was given a card by her in the garden. In the garden, she gave me a card. She gave me a card in the garden, right? So you can see that the model is basically saying all these three sentences, they mean the same thing because they lie so close to each other in this, in the two-dimensional space or in even the high-dimensional space. So semantically, when you do translations, the model basically figures out these are all the same things. Or she was given a card by me in the garden. So it's basically saying she was given a card by me in the garden versus she gave me a card in the garden. It thinks that these two sentences are further away from each other. Or in the garden, I gave her a card. I gave her a card in the garden. So depending on who's giving a card to whom, the model is able to separate these sentences. And again, of course, it depends on what task you're trying to solve. This task was just doing machine translation, right? So it found these representations, which was surprising to a lot of people. This was a paper published back in 2014, and I think it inspired a lot of people to look at these sequence-to-sequence models. Because, there is nothing difficult in this model. It was actually surprising. Some people thought that, it's like you have this big hammer, and you just say, I'm just going to inject one sequence into a recurrent network, and I'm just going to produce the other sequence without having any knowledge of linguistic, without using any phrase-based translations, without using, any sort of prior knowledge. Kind of almost like a brute force way. You just come in, you have this big hammer, and you just hammer it. And it works surprisingly well, right? So your blue scores are a whole bunch of baseline systems were pretty good. And in today's systems that you see in Facebook, in Google, a bunch of other IT companies, they are using these neural machine translation-based systems, which was quite surprising. Because if you look at the traditional machine translation community, they've been doing it for over 20, 30 years. And it's very, very hard because people tune these models so well, right? It's very hard to beat. But I think that now with these neural MT systems, they do much better because it's a very much data-driven approach as opposed to hand-tuning approach. So a couple of concerns you should keep in mind. First of all, we'd like to use language models, right? We'd like to give it a little bit of some prior knowledge. Like if we do translation from English to French, and we have almost an infinite corpus of French sentences, not just the translations, but just, you go to Wikipedia, and there's lots of Wikipedia in French. So how do we incorporate language models? And there's been some work on trying to use, so there was a work on using monolingual corpora in the neural machine translation. So what happens here is that you essentially have some language model and you're combining it with predictions coming out of machine translation system. And there is a way of trying to figure out, which do you trust and how do you combine them. The second thing you have to worry about is out of vocabulary words, right? So sometimes when you're doing translation, or even when you're doing language modeling, sometimes you see a word that you've never seen before. So what do you do? So people have used character-based embeddings, right? So if I give you a word that you've never seen before, you can use a character-based embedding. So you have a neural network that basically reads one character at a time. And now you get the representation of the word. That works really well, particularly if somebody is misspelling things. Right? If you misspell one particular character, then the model can still pick up on the representation of the word, which is pretty interesting. So there's a lot of work on trying to combine word-level embeddings and character-level embeddings, particularly for dealing with out-of-vocabulary words. Sequence length, again, that's a problem. If your sequence is very long, these models don't work that well, because they tend to forget what happened in the past. Let me show you a couple of examples of this particular system, which is, we've talked a little bit about it, is image captioning, right? And again, the idea is sort of, just like you're doing translations from French to English, here we're going to be doing translation from images to English, right? And again, this comes into the exact same framework of sequence-to-sequence framework, right? Which is the following. I give you an image. You extract the representation of the image using some form of a convolutional network. There are a whole bunch of them now, like VGG. There is ResNet. There is Inception. There's like a few standard ones that work fairly well. So you get the representation. You get some vector W, and that forms the initial state, right? So the initial state of your recurrent network is just a representation of the image. That's why you don't have any input that's coming into the first hidden state. Or you have some kind of predefined token to have it as an input. But really, it's just an empty input. So based on the image, you start making a prediction. And the word here basically says air. That's the first word. And again, here you can be, a lot of times people would be using a beam search, typically beam search of size 20. So you pick the 20 most probable starting words, and then you expand each one of them. You compute the probabilities, you re-rank, you pick the top 20 and so forth. So you're always maintaining a buffer of 20 possible alternative explanations. And now you basically say, well, you predict the word A, and then you plug it in here. That's your prediction. Given the word A, you're predicting the word cake. Again, given the word a cake, you're trying to predict with. And given the word a cake with, you're trying to predict a, right? And such. So you go and you make these predictions. And the interesting thing to note also, it's not shown here, is that there's also end of sentence token, right? Which is another, you can think of it as another word, which is once you reach end of sentence token, then you stop, right? You don't have to predefine a priori what the length of a sentence should be. You're just generating the words up until you generate the end of the sentence token. It works pretty well. If you're interested in this kind of stuff, there is a whole bunch of image-to-text models. So you can just download and play with these models. People have done, if you Google, there's a lot of different libraries that people have built for this kind of stuff. So you can just go and try training it. I've shown you some of these examples. These are some examples that that you can generate, which is pretty interesting, right? So these are pretty good ones. Here's some examples just to show the human versus the best model. And the best model was basically, I think that the authors that I've shown before, they've trained on a whole bunch of models, and they pick the best one in terms of measuring log probability of the correct sentence. So see, a human would say a close-up of 2 bananas with bottles in the background, and the best model says a bunch of bananas and a bottle of wine. So it's not perfect, right? Because it doesn't understand that this is beer, it's not wine, but nonetheless. Here's another example. a human would say, woman holding up a yellow banana to her face, and the best model is woman holding a banana up to her face, which is pretty good, right? Here's another one. A man outside cooking with a sub in his hand, and the best model says a man is holding a sandwich in his hand, right? So I guess it doesn't really know that this person is cooking, it's just holding a sandwich. This is another example. Someone is using a small grill to melt its sandwich. That's how humans would do it. The model says a person is cooking some food on a grill. So it's not as precise, but it's pretty good. Here's another example. A blue, yellow, and red train travels across the tracks near the depot. And the best model is blue and yellow train traveling down the down train tracks. A blue and yellow. I'm not sure why humans would say blue, yellow, and red train. There's a blue and red, but not sure why the yellow isn't there. So sometimes when people also provide, these captions, they might be confusing. That, many times they're not perfect either. But you can see that, now these systems are getting to the state where they can actually be fairly accurate for being able to generate reasonable descriptions of what's going on in the images. And there's now a whole subfield of visual question answering work where, I ask you the question about this image and you're supposed to give me the answer, right? Which is sort of an extension of the caption generation work. Here's another example, which is people went a little bit, once you realize, you can just model any sequence to any other sequence. So here they've tried to basically do, your input is like a Python code, and your output is the prediction what the output of this Python code would be, right? So I give you like j equals, and then here I'm just counting, and then you're printing the number, and your target is, that's your target. So your input is really just a character-based RNN, right? It just reads just characters, and it's supposed to figure out what this program is executing. And I think they've shown pretty reasonable results, like 70–80% accuracy, to being able to read and be able to predict what the output of the program should be. This is based on characters. And then they basically showed this thing. This is your input. Then the model will predict this is your output, right? So if garbage in, garbage out, basically, which is fine. So that was kind of nice, right? Now here they basically were predicting character base. So they were not predicting this particular number. They were actually predicting spitting out characters like 1, 5 in this case, right? So it's kind of pretty much applying sequence to everything. Yes? Your input is just a bunch of characters.
Oh, so you're not like grouping functions together?
No. Your input is really like character ID for J. You think of it as one of K encoding scheme. And in this case, depending on, what's the vocabulary, maybe it's of 100 or 200 characters, possible characters. And you really just give the machine, you can, if you think of it as just flattening the whole thing, you basically just have a sequence J equals 85, 84, F, O, R, X, E, I, N, R, E. And so you just give it a whole bunch of sequences and you output the target sequence.
How can you get like blocking and it's like under a for loop, how can you tell what's inside the for loop?
Well, it figures it out on its own. That was the experiment. I think that here, maybe they also use the white spaces as a character as well, right? But at the same time, it sort of figures out that, based on training a whole bunch of examples, it basically learns that there's something that's called for loop, there's something that's called print, and just looking at the input outputs, you can have predictions. It doesn't mean there is no guarantees that it will work, right? You can't really kind of like have a certificate of verification that for this example it will give you the right answer, but they've shown that in many cases it actually does pretty reasonably well. Yes?
In this problem setting, is it helpful to have multiple representation for the program language?
Yeah, absolutely. I mean, it's obviously like, we know this is a deterministic program, right? These are languages in, what is it, Python. Maybe if you have a specific representation, you know, for specific token for example, a specific token for print, and have some kind of hierarchical nature of what the for loop does. I think that here they just basically did a brute force thing, right? Just input bunch of characters, output bunch of characters. Can you map it? In many cases you can. Yes.
Also, is there any direction of research to prevent that kind of malicious input in the
What would be malicious input? Your input.
I mean, the third one, like, there's some really.
Yeah, I mean, probably, yeah, you can. You can probably like look at the distribution of the inputs and say this is a garbage input. There is a way of potentially doing that. But here they just wanted to show that, you know, based on this input, that's what the output is. Yes, maybe one more question and then.
For the image to caption project, only use a pre-trained model to extract the feature.
That's right.
Do you adjust the weight of a pre-trained model during training?
Yes, so it depends on how much data you have. If you have a lot of data, then adjusting the feature representations for the image model would help. Typically, there aren't a lot of data sets. So for the caption generation systems, you typically have on the order of like, you know, 80,000, 100,000 examples, in which case it's not enough to actually train the image model itself. So in many cases, the image model is fixed. You just have fixed length representations, and then you're training on top of it, right? Yes, maybe just one last.
So the image to caption data set is like a 1-to-1 mapping from image to a sensing.
That's right.
So that depends on the quality of the stream.
Sure. Yep. But the model will be able to learn. So if I go here, for example, the model will be able to learn because you just have pairs of images and sentences. And if for the similar image, maybe for a similar image, maybe there's another image of a cake, you might have a shorter description or might have a longer description. The model just learns to generalize, right? So I think that's fine. So now, one of the problems with these models is the fixed size embeddings, right? And whenever you have long inputs or long outputs, these models don't tend to work that well, right? So for example, here you're seeing that as the sentence length increases, the quality of the BLEU score is actually going down. So you can't really translate long sentences. Or this is another example. These are test sentences sorted by the length. And if you look at, you know, a complicated LSTM with multiple layers versus a baseline, which is a simple model, for very like sentences of length 79, they're doing about the same. So these models don't work that well for long sequences. In which case, there is a mechanism called attention, which allows you to kind of allows you to adaptively compute the representation of the input sequence. So let's look at this particular here, right? So here, same embedding informs the entire output, right? It really is. I've just read an English sentence, and that's it. That's my representation of the sentence. And when I'm trying to translate, I'm only base my translation on this input alone. For some tasks, you might want that. So for example, when last class we talked about skip thought representation. So we really wanted to see, here's the sentence, I just want to have a vector representation of the sentence because I want to do sentiment analysis or I want to do retrieval of similar sentences or for whatever purposes, I just want to have a fixed length representation. But for other things like translation, that might not be the optimal. So you need to capture all the information about the input regardless of its length, right? So in this case, you're forcing the model to remember the whole sentence. Imagine your sentence contains, 80 words. I just go and give you like my whole story for 80 words of what happened, and now I'm asking you to translate the whole thing, which is difficult for these models to do. So the question is there a better way to pass the information from encoder to the decoder, right? So somehow, if I'm encoding things, is there any better way for me to take into account what's an encoding is doing and pass it to the decoder? And it turns out that there is a way to do it, and it's called attention. It was developed by Bahtanau back in 2015, which is pretty recent. So the idea is the following. When I try to predict a particular target, in this case YT, think of it as some translation. What I'm going to do is I'm going to look at my entire input. I'm going to assign probabilities, these alphas, to every single input. And these alphas are going to be probability of each particular word or each particular time component, how much it matters. Maybe this alpha is going to be 0.001, but this alpha is going to be 0.98, which will basically say, you know what, I need to get this representation and pass it to predict, what the word might be. For example, if I'm doing translation here, it says, the agreement on the European Economic Area was signed in August 1992. So if I give you this sentence, and now I'm trying to predict, I'm trying to predict the word Accord sur la zone économique. So I'm trying to predict the word economic, right? Do I need to look at the entire sentence? Or do I just need to look up at the appropriate part of the input? So if I look at the attention really focuses on two things: European economic, right? So you see that over here. So it really is basically saying, when I'm trying to translate this particular word, all I need to look at only one part of the input, not the entire input, right? And as you're training all of these alphas, all these coefficients, so you're basically trying to train what part of the input is important. All right, and so you kind of like, for example, 1992. If I'm trying to predict 1992, do I need to look at the whole sentence? No, I just need to look at 1992 in my English version, right, to predict the French one, because it's the same thing. And that's exactly how traditional translation systems are working, because you're doing something called alignment. You basically say, I'm translating this word into this word, and I'm translating this word into this word, right? So now you're basically trying to learn the alignment between the input and the output. That's essentially what the attention is doing. The beauty of attention mechanism is that you can actually train it. You don't have to specify the alignment by hand, but you can learn what these alphas are as an objective, right? Your objective is always to do the correct translation, right? And you're trying to figure out what is this alignment should be so that I can translate one sentence into another sentence and I can be as accurate as possible. That's the beauty of a lot of these approaches, is that I don't really have to specify. And then based on that, there is now a lot of work on something that's called visual attention, which is really trying to say, here is an input. If I try to generate a sentence or I try to do something else with the input, which part of the input I should be paying attention to? And there is a lot of work in psychology that we don't kind of look at every single pixel in the image, right? We kind of scan very quickly and focus on important parts of the image. And there's been a lot of studies where people try to say, well, how can we model this attention? Can we actually get like eye trackers? People would like create an eye tracker with a specific device that would try to register where you're looking at. So they show an image and just see where the person is looking at, and try to model that. Here, the interesting piece is that you're trying to learn where the model should be looking at on its own in order to achieve a particular goal, like a classification accuracy or translation accuracy or whatever your target is, right? Which is, I think that in my view, it's a very nice kind of objective, because you don't have to specify what people are doing or how we're doing it. You're really saying, I just want to get the right answer. So do whatever you need to do to get me the right answer. Yes?
So where is the data to find environment regions to attend? So isn't that X has the information about it?
Yep. All you say, you're basically saying, I need to translate this sentence into this sentence. Find me attention mechanisms that can help me. That's all. Or like as part of the optimization strategy, because what this is the way you think about this is that you take these pieces, you compute these probabilities, you add them up, and now that's the representation you use to predict YT. And now intuitively, when I compute the gradients, I know what the correct YT is, right? At the training time, I know the correct target. So I'm going to back propagate through this mechanism and update my alphas, which is again a parametric functions of the hidden state. And I say, can you make my alphas be better? Because if my alphas are different, I can predict YT better. So it's always about trying to adjust what your attention mechanism is in order to predict correctly the target. The whole system is differentiable, so it's just one big optimization objective, right? So a lot of people initially were also thinking about, how do I find these attention weights? I need to do alignment, right? Because that's what people would do. You would align economic with economic. You would align European with European, right? And so that when you do translation, it's almost like you do word by word translation. Then you try to come up with a phrase-based alignment and try to come up with the answer. These are traditional machine translation systems. Here you are basically saying, no, I'm going to learn what the alignment is. Yes?
Is the alpha a trainable?
Yes.
Are they fixed as Archimedes matrix or?
Yeah, we'll come to that. We'll come to that. Alphas are going to be trained parameters. They're parametric parameters of the hidden states. And these are just numbers that sum up to 1. They're just basically assign importance to each of the input features. Yeah. So let's look at the attention, and let's look at the attention, how it works. So remember, we have, just as a reminder, we have sequence to sequence, right? So this is, you read the whole piece into your neural network, recurrent neural network, and then you predict the whole output. The attention is basically doing the following. You have an encoder, but now you have attention-based embedding. So at every time step, you're going to have a different embedding. So a different embedding computed for every output step. Okay? For example, if I look at this H1 is also going to be dependent on the attention, and H3 is going to be dependent on attention, and so forth. So if I look at the hidden state representations are going to be functions of attention mechanism. In particular, when I look at, for example, here, when I look at my input and I look at my first hidden state, right, I'm going to compute some function f, which is going to be a function operating on the input and a function operating on H1, right? That will influence what am I predicting, and it's also going to be influencing what the next hidden state should be. Okay? And this function is what we call sometimes the attention-based function. So now if I go and try to predict, again, at the next time step of H2, again, different function of the input, and H2 is going to be predicting Y, and it's also going to be influencing my hidden state, and so forth. Right? So your attention is always computing this function, and so that allows you to, this function will, depending on what you're looking at, depending on the hidden state, it will change attention over here as well. What am I looking? Right? Intuitively think of it as this way. If H1 has to do with something like, let's look at this one. Let's say H2 has to do something with economic. Like I said, the world economic, the next word should be forum, most likely, right? If I say the world economic and I'm trying to predict what the next word should be, my attention will try to find, like, is there a forum here somewhere? Right? And if there is a forum, that gives me evidence that I should be predicting forum. So, right, is this sort of intuitively clear what's going on? Yes?
So we assume that every input has an impact on every element of the output.
That's right. So input, different function of the input and different function of the hidden state will have effect on the output. Every output. Before, we didn't have this. Before, once you have the embedding, that's it. That's the only thing. It's constant. And it affects all the outputs. Right? So here it's dynamic. It really is impacting the output. So let's look at the attention-based embeddings. So what you're trying to do, let's say you have, in an encoder, let's say you have 4 words. You have some embeddings of those words. And what you're doing is you're doing some linear blending of these embeddings, right? So you're trying to have some linear combination of these embeddings. But how do you produce these coefficients, these attention vectors for these blending, right? And this is content-based coefficients based on the query state HI and the embedding states of RNN. So HI is in the decoder. What is it that you're predicting in the decoder? Depending on what you're trying to predict, you're going to try to compute which of these states of the encoder, which of the embeddings of the encoder are going to be important for you, right? So think of it as that the encoder has a bunch of states, and all you're trying to do is you're trying to find linear combination of these states. In traditional systems, you just put an RNN on top of them and say, that's it. There's one fixed representation. Now you have these 4 states, if you have 4 words, and depending on what the output is, you're trying to pay attention more to here or to here. So this is the most commonly used one, is something that's called dot product attention. So let's look at precise example. Let's say I have an input, I am a cat. And let's say you're trying to translate it into French, or you're trying to predict the next sentence, whatever is your output sequence is. So the input RNN states would be E1, E2, E3, E4. Okay? So these are states of a recurrent network, 4 states, because you have 4 words. Now the decoder RNN state at time I is going to be HI. So let's say at step number 1, I have some hidden state, or at step number 2, I have some hidden state, HI, right? What I'm going to do is I'm going to compute the scalars, HI transpose E1, HI transpose E2, and so forth. This is essentially looking at cosine similarity, or it's looking at the similarity or relevance between encoder steps and the query, where the query is the decoder states, right? So if the decoder states talks about world economic something, right? What do you think, maybe these words are going to be more relevant and these words are going to be less relevant. So you're going to be paying attention more to these embeddings and just ignore these ones, right? So it really is, when you're trying to output something, you're just trying to see your output states, the decoder of a recurrent network, how close it is to your encoder states. You normalize them with softmax probability so that they all numbers between 0 and 1, and they sum up to 1. And now you basically get these weights, 0, 0.05, 9, 0.05. So you're basically saying this word is very important whenever you're doing decoding. And so notice that you're learning everything. You're learning what these E's are. These are word embeddings. You're learning what the hidden states are, right? So that gives you the attention. So that's part of the attention mechanism. You're learning what these attention weights should be. Because whenever you produce something at the output, you're just looking at the similarity, what you're trying to predict versus, if I talk about Obama and I'm trying to predict Obama, maybe the hidden state basically say, I'm going to predict Obama. And now I'm going to try to rely on the input, and I'm going to try to look at my input and say, is there any input that talks about the president or Obama, right? Which will pay more attention to those tokens to make a prediction. That's why you have such a nice alignment if I go back here, over here, right? And in many cases, it's almost 1-to-1, because if I'm trying to predict 1992, I really just need to pay attention to 1992, one token, right? So these softmax probabilities really turn out to be close to 1. Right. Is that clear? It's a very simple idea. It's almost like doing content-based retrieval. I'm trying to predict some hidden state, and I'm just looking at similarity of all the input hidden states, and I'm just choosing the most important ones. And notice that the whole thing you're training, right? So you're training to learn what these weights should be. So this is content-based attention. You basically have some 10H, which is your hidden state. You take it a dot product, you do softmax, and so forth. So there's been a number of works on something that's called neural Turing machine, memory network, something that we will revisit later in this class, maybe dedicate one lecture to memory. But here, the idea is that given some key and some scalar S, some people use S again as a hyperparameter, or something that can be emitted by a controller, you use weighting over the memory location. So again, the idea here is that's a more general concept, that if I'm trying to do some form of retrieval, I can take the representation of my query, I can take representation of some of the states that I have, I can look at the dot product, renormalize via softmax, using some cosine similarity, and then have a retrieval mechanism. So these kinds of ideas have been extended to working with memory. like things like memory networks and neural Turing machines and such. And again, we're going to have probably like half of the class dedicated to using memory mechanisms for reading comprehension and for reinforcement learning and such. So this concept is very simple, but you'll see a lot of it in research, because everything is differentiable. That's what makes it kind of interesting. Other strategies for attention. So people have started looking at multiple ways of doing attention. It's something called tensored attention, where instead of multiplying two things, you can multiply multiple things. You can create a tensor, depending on multiple information that's coming in. You can have multiple heads, basically meaning that instead of, right now, which is basically based on the hidden states of the decoder to produce one softmax. But maybe you can produce multiple softmaxes and aggregate information that way. People have looked at pyramid encoders that I'll show you some examples where your encoder is not just a flat thing, but it's like a pyramid. People have looked at hierarchical attention. So here, instead of using softmax over the whole thing, you're trying to build some hierarchical softmax. Hard attention mechanisms is, this is something that we've done, which is kind of looking at sampling strategies, which is to say, instead of looking at, all hidden states in your encoder, just sample one, right? Or pick the most probable one. That can save you time in terms of training speed and inference speed. So there's a whole bunch of different models. I can't go into all of them, but if you're interested in that work, you should look at a lot of these different methods. Whoa. What happened? Let me just show you one example that I wanted to show you, and then I'll let you go. Just bear with me, because I think that it's next class we will take a little bit of time to go over. Next time we'll have take a little bit of time to go over midterms. So I wanted to spend the next 5 minutes just to show you a couple of applications. This is a pretty cool application. It's also a little crazy. But for those of you who are familiar with parse trees and language understanding, one of the big areas is given a sentence like John has a dog, you want to come up with a parse tree, right? You want to figure out where the noun phrase is, where the verb phrase is, and so forth, right? That gives you the syntactic representation of the sentence. So there was a work by Oriel and et al. That basically said, well, can't we just have an input, John has a dog, and just produce a parse tree directly? So really just producing characters, and not the characters, but these individual terms, right? And so they were quite successful in doing that, and they also used attention mechanisms, right? So when you're trying to predict verb phrase here, they've shown that attention kind of is looking at the right parts of the sentence. So when you're predicting a noun phrase, like, John, for example, it really pays attention to John, right? So it's kind of a nice way of doing parsing in real time and very quickly. Here's another example that I just wanted to go through that also shows the attention mechanism. This is, let me just spend another 5 minutes. This is speech recognition. And let's say that this is an audio signal that comes in. And let's say this is somebody saying cancel, cancel, cancel. Right? So what you'd like to do is you'd like to get the representation. Typically, you build some kind of RNN or some DNN that reads the audio signal. And then you push it into the decoder to introduce it to actually compute the transcript, compute the words. Right? And actually, this is done based on the characters. So let's look at how it's actually done. So here, we're going to be seeing prediction derived from attending to a segment of the input, particular segment of the input. Obviously, we're reading from left to right. And this is going to be the attention vector where the model thinks the relevant information is to be found. Okay? Again, it's just sequence to sequence with attention. So here you're predicting C. The next prediction is A. And if you see, it's paying attention to this piece and the piece next to it. Then it's predicting N, and it's basically paying attention to just this particular slice of the audio signal. These are phonemes. It's trying to identify all the phonemes. Can s, and then it's predicting c, but interestingly enough, because we say cancel, 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 it pays attention to this one, because it's in time, but it also pays attention to this and this. So it spreads its attention mechanism, into the future, right? Because it's kind of similar phonemes. And then E, it kind of like looks at, again, this attention, and then it's kind of L, and says L, and it also pays attention to these ones a little bit, right? So again, it automatically figures out when it's transcribing each particular phoneme where it should be. And this is what the attention looks like if you are correctly transcribing cancel, space, cancel, space, cancel, end of sentence, right? So it's kind of nice. This is another example, and I'm going to be done. This is another example of caption generation with visual attention. Precisely the same example. The idea here is that you bin your image, like in convolutional neural network. If I look at the top level feature, the top level feature typically looks at some part of the input, right? And the top level features looks at some other part of the input. So now you're doing attention over top level features, right? Much like you're doing attention in translation. So now this is an example of a system that says a man riding a horse in a field. So when it says the word the first word, if you look at the attention weights, where it's paying attention, it's mostly paying attention to this part. Then it generates men. When it generates the word man, it pays attention to the features that focus on the man, right? So it doesn't really matter. It doesn't pay attention to everywhere else. It's automatically trying to figure out where it should be paying attention. Riding a horse, it tends to focus on the horse's head. These weights have, much higher weight. In, and then in is kind of like vacuous word, right? In and then it's like trying to say in a field. So when it goes a field, it pays attention. It's hard to see, but it pays attention to the surroundings. It kind of ignores the person in the middle. In the field, it kind of looks around, the grass and the surrounding areas. So if you look at these attention weights, when it generates certain words, it pays attention to different parts. So it's kind of interesting, right? Because you can do it in caption, visual attention, you can do it in machine translation, you can do it in speech transcription. So a lot of it is really this idea of automatically learning what input is important and what input is not important, which is fairly powerful idea, and you're not aligning it by hand. Nowhere in these systems you're specifying to the model, when you generate horse, look here. When you generate field, look here. You're really just telling the model, look wherever you want to look. It's up to you to learn that, such that for this image, I'm producing this sentence. That's your input, that's your output. That's the only thing that you're giving to the model. So it has to figure out what it should be looking at in order to correctly produce this output. And this might not coincide how people look at images, for example, which is, again, has to do something with how we think. There was an example of, I wish I had this example to show you. There is a big image with like lake and mountains and, like a big deck. Somebody was taking a picture from the deck. And like in the middle of the image, there's a little tiny boat with a few people, right? And humans would say, oh, there's a bunch of people on the boat and on the lake, right? And the model would say like, oh, beautiful mountains and like nice ocean or something like that, right? So obviously you can see there's different preferences how people would caption something versus based on these systems. Here's another example of what these systems can do. You can try to look and figure out why they're making certain mistakes. So for example, here a woman is holding a clock in her hand. So for this image, that's the caption that the model generates. But if you do it with visual attention, whenever it generates the word clock, it's paying attention to this piece here. So it thinks this thing is a clock, right? Which helped us a little bit to try to identify when the model is making mistakes. Because sometimes you give it an image and it just says something that's arbitrarily like, what is this? If you look at the attention, you say, okay, yeah, I see where the model is making mistakes or where it's confused. Here's another one. A large white bird standing in the forest. So when it generates the word bird, white bird, it really focuses on this thing here. And if you look, it's actually a couple of giraffes. So it kind of mistakes giraffes for birds. So maybe based on that, you should say, well, maybe I should collect more data with giraffes and some animals so I don't make this mistake in the future. But whenever it generates the word forest, I'll show it to you here, it really looks at surroundings, right? And then it's like there was one other very cool image where there was a person jumping off the rock, you know, kind of like jumping, and it's like a background in the forest. And the model would say a person climbing a tree. It's like, why is the person climbing a tree? And if you look at the attention, what the model did is basically completely ignored the bottom of the input, right? And if you ignore the bottom of the input, it really does look like the person is jumping, there's a tree behind. It's a plausible explanation, right? So sometimes it makes mistakes, but using this visual recognition, we can actually see what the model is doing. Okay, so next class, we're gonna continue looking at sequence-to-sequence models, and your second homework is gonna be due next class. What else? And I'll try to show you some examples from the meeting.